I'm so glad you found your way here tonight. Tonight, we'll drift gently through the cosmic nurseries where stars are born, exploring the quiet wonders of stellar birth, from the coldest clouds to the first light of new suns. Welcome to Get Sleepy Science. Wherever you are right now, perhaps beneath a blanket with the lights dimmed low, or gazing toward your window where stars might be visible in the darkness beyond, allow yourself to settle into this shared moment of stillness. Tonight, we'll discover 100 gentle truths about creation. From invisible molecular clouds floating between the stars, to glowing protostars hidden in cocoons of dust, to the moment when fusion finally ignites. If these calm stories about star birth help you unwind or give you a gentle way to end your day, consider liking and subscribing or sharing your thoughts below. A gentle like helps more curious minds drift this way too. One sleepy soul at a time. We'd be grateful. For now, just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting through space where matter gathers slowly, patiently, over millions of years. Where creation happens, not in moments, but across timescales beyond our daily experience. Close your eyes and take a deep breath. You're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through the stellar nurseries where new suns are born. Stars are born inside giant molecular clouds. These clouds are the coldest and densest regions in the space between stars, with temperatures hovering around -440 degrees Fahrenheit, just 20 degrees above absolute zero. A typical giant molecular cloud can stretch across 300 light-years and contain enough gas and dust to form anywhere from 10 to 10 million stars. Most of this material is molecular hydrogen, with about 1% dust made from heavier elements. Our own Milky Way galaxy contains roughly 1,000 to 2,000 of these giant clouds scattered throughout its spiral arms. They drift slowly through space, invisible to our eyes, but glowing softly in the infrared and radio wavelengths that specialized telescopes can detect. Within their cold darkness, the universe prepares its next generation of stars. The gas inside a molecular cloud is incredibly thin by Earth standards. Even the densest cores contain only about 10,000 to 100,000 molecules per cubic centimeter. For comparison, the air you're breathing right now contains roughly 25 billion molecules in the same volume, a density difference of more than 1 trillion times. Yet, this seemingly empty space is dense enough for gravity to slowly overcome the outward pressure of the gas. The cold temperature helps too, keeping the particles moving slowly, making it easier for gravity to pull them together. These clouds were first discovered about 50 years ago, using radio telescopes that could detect the faint signals from carbon monoxide molecules floating in the darkness. Before that discovery, astronomers didn't fully understand where stars came from. Within the giant molecular clouds are even denser regions, called cores. These cores are where individual stars will eventually form. A core might contain between 1 and several hundred times the mass of our Sun, compressed into a region just a few light-years across. The density in a core can reach millions of molecules per cubic centimeter, still far more rarefied than any vacuum we can create on Earth, but dense enough for gravity to begin winning its long battle against pressure. These cores form through various processes. Sometimes a spiral arm of the galaxy sweeps through, compressing the cloud. Sometimes a nearby massive star explodes as a supernova, sending a shockwave that squeezes the gas. Other times, the cloud simply becomes dense enough on its own that gravity naturally takes over. Once a core begins collapsing under its own gravity, the process accelerates. As the gas falls inward, it speeds up, and more mass means stronger gravity, which pulls even harder. This creates what scientists call a runaway collapse, a process that, once started, continues inevitably toward creating something new. The collapse happens from the inside out, with the central regions falling fastest, while the outer layers follow more slowly. The material doesn't fall straight down but spirals inward, because even the slightest rotation in the original cloud gets amplified as it shrinks, the same way an ice skater spins faster when pulling in her arms. This spinning motion will eventually create a flat disk of material around the forming star, a disk from which planets might one day emerge. As the core collapses, something remarkable happens. The gas heats up. This might seem counterintuitive, since molecular clouds are so cold to begin with. But the heating comes from gravitational energy being converted to thermal energy. Each particle of gas falls inward, gaining speed as it drops into the gravity well. When these fast-moving particles collide with each other at the center, their motion energy transforms into heat. The temperature rises from -440 degrees Fahrenheit to hundreds, then thousands, then millions of degrees over time. This process transforms what was once the coldest matter in the universe into something that will eventually become one of the hottest. The very center of the collapsing core becomes a protostar, the earliest recognizable form of a star. At this stage, it's not yet a true star, because its core hasn't become hot enough to fuse hydrogen into helium. A protostar typically reaches temperatures between 3,600 and 5,400 degrees Fahrenheit, hot enough to glow a dull red, but still far below the 10 million degrees needed for nuclear fusion. The protostar shines not from fusion, but from gravitational contraction. It's literally glowing from the heat of its own collapse. This glow, however, is hidden from our view by the thick cocoon of gas and dust surrounding it. The material blocks visible light completely, but infrared radiation can escape, which is why infrared telescopes are essential for observing these stellar embryos. A protostar pulls material from the surrounding cloud through an accretion disk. This is a flattened structure of gas and dust that spirals around the protostar like water circling a drain. Matter from the cloud lands in the outer parts of the disk and then gradually spirals inward, eventually falling onto the surface of the protostar. As this material crashes into the protostar, it releases tremendous energy, heating the protostar's surface. The accretion disk itself can extend outward for hundreds of astronomical units, hundreds of times the distance between Earth and the Sunday. These disks rotate rapidly, with material closer to the protostar moving much faster than material farther out, creating friction and heat throughout the disk. Not all the material falling toward a protostar makes it to the surface. Some of it gets ejected in powerful jets that shoot out along the rotational axis of the disk, perpendicular to the disk itself. These jets can travel at speeds exceeding 200 miles per second, roughly 720,000 miles per hour, far faster than any human-made spacecraft has ever moved. The jets emerge in opposite directions, creating a spectacular double-sided outflow. Scientists aren't entirely certain what drives these jets, though magnetic fields threading through the disk and protostar appear to play a crucial role. The jets carry away excess angular momentum and energy, helping the protostar shed some of the spin it inherits from its rotating parent cloud. Without this process, stars might spin so fast they'd tear themselves apart. When these jets slam into the surrounding gas and dust at high velocity, they create glowing regions called Herbig Haro objects, named after the two astronomers who first studied them extensively. These objects appear as bright, colorful clouds, often with intricate shapes, knots, filaments, and bow shocks, where the jet material collides with slower-moving gas. The collisions heat the gas to several thousand degrees, causing it to emit light that our telescopes can capture. Herbig Haro objects typically extend for several light-years from their parent protostar. They're relatively short-lived on cosmic timescales, lasting only a few tens of thousands of years before dispersing. Yet, during that brief existence, they're among the most beautiful signatures of star formation. The time it takes for a protostar to form depends greatly on the mass involved. A star like our Sun takes roughly 50 million years to collapse from a core in a molecular cloud into a fully formed main sequence star. For more massive protostars, those destined to become stars 10 or 20 times heavier than the Sun, the process happens much faster, perhaps only 1 to 2 million years. The largest stars, with masses 50 or more times that of the Sun, can form in as little as a few 100,000 years, sometimes reaching stellar status in under 500,000 years. Smaller protostars take longer. Those forming stars with only a tenth the Sun's mass might require 100 million years or more. The more mass, the stronger the gravity, and the faster everything proceeds. During the protostar stage, the object is completely hidden within its dusty cocoon. Visible light cannot escape because dust particles absorb and scatter it. However, the protostar and its surrounding material emit copious amounts of infrared radiation, which has longer wavelengths that can pass through the dust more easily. This is why infrared telescopes have revolutionized our understanding of star formation. The Hubble Space Telescope captured early views of stellar nurseries, and the Spitzer Space Telescope, before its retirement in 2020, revealed protostars in infrared light. Now, the James Webb Space Telescope offers unprecedented detail, seeing through dust with clarity we've never achieved before. The dust itself warms up from the protostar's heat and glows in the infrared, creating intricate patterns of light and shadow throughout the cloud. Stars almost never form alone. The fragmentation of a giant molecular cloud typically produces multiple protostars at roughly the same time. This is why we observe that most stars are part of clusters or binary systems. When astronomers look at young star-forming regions like the Orion Nebula or the Serpens Nebula, they find hundreds or thousands of young stars all born from the same parent cloud within a few million years of each other. Some of these stars will remain gravitationally bound as clusters for hundreds of millions or even billions of years. Others will gradually drift apart as the cluster dissolves into the galaxy. Our own Sun was likely born in such a cluster roughly 4.6 billion years ago, but its sibling stars have long since scattered across the Milky Way, and we don't know where they are. Recent observations from the James Webb Space Telescope in 2024 have revealed remarkable details about star formation. In the Serpens Nebula, Webb captured images of protostars with jets that align not only with each other, but with the filament of molecular cloud from which they formed. This alignment suggests that large-scale structures in the cloud influence how individual stars form and orient themselves. The telescope also discovered exceptionally young protostars in the NGC 1333 cluster, some emitting powerful jets that ionize surrounding gas, making it glow with distinctive colors in the infrared. These findings are helping astronomers understand the earliest stages of stellar birth with unprecedented clarity. Webb has also identified free-floating planetary mass objects in star-forming regions, objects that are 5 to 10 times more massive than Jupiter, but appear to have formed like stars rather than planets. These discoveries from 2024 blur the line between what we call a star and what we call a planet, revealing that nature produces planetary mass objects through at least 2 different mechanisms. Some form in disks around stars, as Jupiter did in our solar system. Others form from the direct collapse of gas clouds, the same way stars do, but without enough mass to become true stars. These free-floating worlds drift through space without orbiting any star, cold and dark, witnesses to the diverse outcomes of stellar birth processes. As a protostar continues gathering mass, it eventually enters what's called the Tauri phase, named after the first star of this type, discovered in the constellation Taurus. Tauri stars represent a bridge between protostars and main sequence stars. They've cleared away much of their dusty cocoons and become visible in optical light, but they haven't yet begun fusing hydrogen in their cores. These young stars are extremely active, with strong stellar winds blowing matter away from their surfaces at hundreds of miles per second. They also exhibit dramatic brightness variations, flaring up and dimming unpredictably as material from their accretion disks falls onto their surfaces in irregular bursts. A Tauri star might remain in this phase for several million years before settling into stable hydrogen fusion. The transition from protostar to true star occurs when the core temperature reaches about 18 million degrees Fahrenheit. At this temperature, hydrogen nuclei have enough energy to overcome their mutual electrical repulsion and fuse together, forming helium and releasing tremendous amounts of energy in the process. This is nuclear fusion, the same reaction that powers a hydrogen bomb, but sustained and controlled by the immense gravity of the star. Once fusion begins, the star's contraction stops. The outward pressure from fusion energy balances the inward pull of gravity, creating what physicists call hydrostatic equilibrium. The star has reached the main sequence, the stable phase where it will spend most of its life, potentially for billions of years. Not all collapsing cores become stars. If a core contains less than about 75 to 80 times the mass of Jupiter, roughly 0.075 to 0.08 times the mass of our Sun, it will never become hot enough in its center to sustain hydrogen fusion. According to recent calculations published in 2023, the precise hydrogen-burning minimum mass is about 0.075 solar masses, or approximately 78 Jupiter masses. Objects below this threshold are called brown dwarfs, sometimes nicknamed failed stars. They're too big to be planets, but too small to be stars. Brown dwarfs do fuse deuterium, a heavier form of hydrogen, but only for a few million years before running out of fuel. Brown dwarfs gradually cool and fade over time. Without sustained fusion to produce energy, they simply radiate away the heat from their formation, slowly growing dimmer and cooler across millions and billions of years. They emit most of their light in the infrared spectrum, glowing with a dull red or even magenta color that would be difficult to see with human eyes. Astronomers estimate there might be as many as 100 billion brown dwarfs in the Milky Way galaxy, nearly as common as stars themselves. Most remain undiscovered because of their extreme faintness. Some brown dwarfs have even been found with their own planetary systems and dust disks, miniature solar systems, orbiting objects that aren't quite stars. The James Webb Space Telescope may have discovered something remarkable in 2024, evidence of population 3 stars, the universe's very first generation of stars. These ancient stars would have formed when the universe was only a few 100 million years old, made purely from hydrogen and helium with no heavier elements at all. The suspected detection comes from observations of a galaxy cluster, where light signatures match what theorists predict for these primordial stars. Population 3 stars would have been enormous, perhaps several hundred times more massive than our Sun, burning bright and hot, but living for only a few million years before exploding as supernovas. Their explosions scattered the first heavy elements into space, seeding future generations of star formation. Astronomers using the Euclid Space Telescope confirmed in 2024 that star formation in the universe has already peaked. We live in a cosmos past its prime of stellar birth. The rate at which new stars form has been declining for billions of years and will continue to decrease. The universe's coldest, densest molecular clouds are gradually being used up, and new clouds aren't forming as rapidly as old ones are consumed. In the words of researchers, the universe will simply get colder and deader from this point forward. Eventually, trillions of years in the future, star formation will cease entirely, and the cosmos will be populated only by the slowly cooling remnants of the last generation. The very first stars in the universe formed under conditions very different from today. There were no planets at that time because planets require heavier elements like carbon, silicon, iron, and oxygen. These elements didn't exist in significant quantities until after the first stars had lived and died. The cosmic noon period, roughly 2 to 3 billion years after the Big Bang, saw the most intense era of star formation in cosmic history. Galaxies were forming stars at rates hundreds or thousands of times faster than the Milky Way does today. Molecular clouds collided and merged, triggering massive bursts of stellar birth. The universe during that era would have been far more luminous, crowded with young, hot stars, radiating powerful ultraviolet light across intergalactic space. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion constellation, is one of the closest and most studied star-forming regions. It lies about 1,350 light-years from Earth and contains roughly 700 stars in various stages of formation. The nebula itself glows with the light from 4 massive young stars called the trapezium, which formed less than 1 million years ago and now illuminate the surrounding gas with intense ultraviolet radiation. The Hubble Space Telescope has captured detailed images of protostellar disks within the Orion Nebula, some already losing their material as the radiation from nearby hot stars evaporates the gas. These are planetary systems trying to form under harsh conditions. In 2024, a survey of the NGC 1333 star cluster using Webb's instruments revealed at least 6 new free-floating planetary mass objects and discovered a rare brown dwarf binary system where 2 substellar objects orbit each other. The survey also reanalyzed 19 known brown dwarfs in the region. Remarkably, despite the telescope's sensitivity, no objects lighter than about 5 Jupiter masses were detected. This finding suggests that there may be a natural lower limit to how small an object can be and still form through the star formation process rather than forming as a planet in a disk. The boundary between stars, brown dwarfs, and planets continues to fascinate and puzzle astronomers. Stars can continue forming for a long time within a single molecular cloud. The cloud doesn't collapse all at once, but rather in waves, with different regions becoming dense enough to form stars at different times. A giant molecular cloud might produce stars over a span of 10 to 20 million years before the energy from the newly formed stars disperses the remaining gas, ending the process. The most massive stars play an especially important role in this dispersal. Their intense radiation heats the surrounding gas, and their powerful stellar winds push material away. When the most massive stars finally explode as supernovas, the shockwaves can shred what remains of the cloud, scattering it back into interstellar space. The efficiency of star formation is surprisingly low. A giant molecular cloud containing 100,000 times the mass of the Sun will typically produce only about 10,000 solar masses worth of stars, a conversion efficiency of roughly 10%. The rest of the material gets dispersed back into space before it can collapse into stars, blown away by stellar winds, radiation pressure, and supernova explosions from the first generation of massive stars. Some gas returns to diffuse interstellar space, where it may eventually be swept up into a new molecular cloud millions of years later, ready to participate in another cycle of star formation. Matter recycles through the galaxy, alternating between diffuse gas, dense clouds, and stars across billions of years. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. The molecular clouds where stars form are not uniform. They're filled with intricate structure, filaments, sheets, bubbles, and cores embedded within a more diffuse background. Recent observations, particularly from the European Space Agency's Herschel Space Observatory, revealed that filamentary structures are ubiquitous in molecular clouds. These filaments are long, narrow strands of dense gas. like cosmic threads, often many light-years in length, but only fractions of a light-year wide. Stars preferentially form along these filaments, in the densest knots where multiple filaments intersect. The filaments themselves might form through turbulent gas motions, gravitational instabilities, or compression from magnetic fields threading through the cloud. Magnetic fields play a subtle but important role in star formation. The gas in molecular clouds is partially ionized, meaning it has a small population of electrically charged particles. These particles couple to magnetic field lines that thread through the cloud. The magnetic fields provide a small amount of support against gravity, slowing down collapse and channeling gas flows along field lines rather than letting it collapse freely in all directions. As the cloud contracts, the magnetic fields are dragged along and become more concentrated, growing stronger. Eventually, however, gravity wins, and the magnetic fields must either dissipate or be trapped in the forming star. The Eagle Nebula, made famous by Hubble's iconic Pillars of Creation photograph, is an active star-forming region about 6,500 light-years from Earth. Those pillars are structures of dense gas and dust where new stars are currently being born, hidden within the columns. The pillars formed when intense ultraviolet radiation from nearby massive stars evaporated the surrounding, less dense gas, leaving behind these dense towers. At the tips and within the pillars themselves, small globules of even denser material continue collapsing into protostars, even as the radiation from outside gradually erodes the pillars away. It's a race between star formation and destruction, with both processes happening simultaneously. In 2024, researchers studying the far edge of the spiral galaxy, M83, made an intriguing discovery about where stars can form. They found 23 molecular cloud cores at the very outskirts of the galaxy, regions where the gas density is very low by galactic standards. These cores were birthing stars in an extreme environment where astronomers didn't expect to find star formation at all. The discovery suggests that molecular clouds have hearts, extremely dense cores that can form stars even when the surrounding envelope of gas is thin or absent. This finding challenges our understanding of the minimum conditions necessary for stellar birth. The Carina Nebula, located roughly 7,500 light-years away, contains some of the most massive stars known in our galaxy, including several that are more than 100 times the mass of the Sun. These giant stars formed relatively recently, within the last few million years. Their intense radiation has carved enormous cavities in the surrounding gas, creating dramatic landscapes of pillars and bubbles. The James Webb Space Telescope captured stunning infrared images of a region within Carina called NGC 3324 in 2022, revealing hundreds of previously hidden protostars embedded within the dust. The images show the complex interplay between new stars being born and massive stars destroying their parent cloud. When a massive star forms, it produces so much ultraviolet radiation that it creates what astronomers call an H2 region around itself. This is a bubble of ionized hydrogen gas, glowing brightly with a characteristic red color from excited hydrogen atoms emitting light. These regions can be enormous, stretching across dozens or hundreds of light-years. The radiation pressure and stellar wind from the massive star push on the surrounding gas, compressing it at the edges of the bubble. Paradoxically, this compression can trigger new rounds of star formation in a process called triggered or sequential star formation, where the birth of one generation of stars initiates the birth of the next. Dust grains in molecular clouds, despite making up only about 1% of the mass, are crucial to star formation. These microscopic particles, typically less than 1,000th of a millimeter across, provide surfaces where hydrogen atoms can meet and combine into molecular hydrogen. Without dust, the conversion of atomic hydrogen to molecular form would be extremely slow, and molecular clouds might not form at all. The dust grains are made of materials like silicates, carbon, and ices of water, methane, and ammonia that have condensed in the cool outer atmospheres of old stars and been blown into space. They're cosmic recycling, essential components in the ongoing cycle of stellar birth and death. The rotation of a collapsing cloud creates a fundamental problem for star formation. As the cloud shrinks, conservation of angular momentum should cause it to spin faster and faster, eventually spinning so rapidly that centrifugal force prevents further collapse. Yet, stars do form, somehow solving this angular momentum problem. The solution involves several mechanisms. Material is thrown off in jets. Angular momentum is transferred outward through the accretion disk via friction and magnetic fields, and some material is expelled by stellar winds. Together, these processes allow the forming star to shed enough spin that it can continue contracting without tearing itself apart. Binary stars are extremely common, perhaps even more common than single stars like our Sunday. Recent estimates suggest that more than half of all Sun-like stars are part of binary or multiple star systems. These systems form when a single collapsing core fragments into two or more pieces during the collapse process, each piece forming its own protostar. The resulting stars orbit their common center of mass, bound together by gravity for billions of years. Some binaries are very close, with the two stars separated by distances less than the diameter of a single star. Others are wide, with companions separated by thousands of astronomical units, barely gravitationally bound to each other. Supernova explosions from massive stars can both trigger and disrupt star formation. The expanding shockwave from a supernova compresses nearby molecular clouds, potentially triggering the collapse of cores that might not otherwise have formed stars. At the same time, the blast sweeps away gas that could have formed additional stars, clearing out regions of space. Supernova remnants also inject heavy elements into the interstellar medium: carbon, oxygen, iron, and dozens of other elements forged in the star's core and during the explosion itself. This enriched material eventually becomes incorporated into new molecular clouds, ensuring that each generation of stars is born with a slightly higher abundance of heavy elements than the previous generation. Protostars emit most of their light in the infrared, but they also produce X-rays. These X-rays, first detected by NASA's Einstein X-ray Observatory decades ago, come from intense magnetic activity on and around the protostar. The magnetic fields, twisted and tangled by the protostar's rapid rotation and convective motions, occasionally snap and reconnect, releasing bursts of energy that heat gas to millions of degrees. This same magnetic reconnection process creates solar flares on our Sun, but protostars and young Tauri stars produce X-rays 100 to 100,000 times stronger than mature stars. Like the Sunday, the intense radiation can affect planet formation in the surrounding disk. The small Magellanic Cloud, a dwarf galaxy orbiting our Milky Way, offers a unique laboratory for studying star formation. Its gas has lower concentrations of heavy elements compared to the Milky Way, making it similar to conditions in the early universe when the cosmos was younger and less enriched with metals. In 2023, the James Webb Space Telescope studied NGC 346, a star-forming region in the small Magellanic Cloud, and found that despite the low metal content, the region is producing stars actively and efficiently. The observation helps astronomers understand how stars formed during cosmic noon, when the universe had fewer heavy elements than it does today. Star formation rates vary dramatically across different types of galaxies. Spiral galaxies like the Milky Way form new stars at a relatively steady pace. Our galaxy produces roughly 1 to 3 solar masses of new stars per year. Elliptical galaxies, which contain older stellar populations, have largely stopped forming stars, having exhausted most of their cold gas long ago. Starburst galaxies, often the result of galactic collisions or mergers, can form stars at rates hundreds or thousands of times faster than the Milky Way. These bursts are short-lived on cosmic timescales, typically lasting only tens of millions of years before the available gas is used up or blown away by stellar feedback. The Taurus molecular cloud, located about 430 light-years from Earth, is one of the nearest star-forming regions and has been extensively studied. Unlike more violent regions like Orion or Carina, Taurus is relatively calm, forming only low-mass stars similar to or smaller than our Sunday. The region contains hundreds of young stars and protostars scattered across about 65 light-years. Many are Tauri stars that have already cleared their cocoons and become visible. Others remain deeply embedded in dusty cores. The Taurus region is so close that astronomers can study individual protostars in remarkable detail, measuring their masses, temperatures, and rotation rates with precision. Only about 10% of protostars surrounded by disks survive to become stars with planetary systems. The rest of the disks are destroyed by intense radiation from nearby massive stars before planets can finish forming. The Hubble Space Telescope has observed this process in action in the Orion Nebula, where powerful ultraviolet light from the trapezium stars is evaporating the outer layers of protostellar disks, leaving behind only small, dense cores. These prematurely exposed proplyds are being eroded away, their material streaming into space. It's a gentle reminder that stellar birth occurs in energetic neighborhoods, where some beginnings follow different paths than others. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I, and everyone listening in the quiet dark, floating through facts like asteroids, drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The first few million years of a star's life are the most chaotic. Material rains down from the accretion disk in irregular pulses. Jets blast outward at hundreds of miles per second. The protostar's brightness varies wildly as it swallows clumps of matter. Magnetic fields twist and snap. Eventually, though, the disk thins as most of its mass falls onto the star or is blown away. The jets weaken and stop. The star's brightness stabilizes. What was once hidden in a cocoon of dust emerges as a visible young star, still not quite settled, but far calmer than its turbulent beginning. Planets form in the same disks that feed growing protostars. Tiny grains of dust stick together through static electricity and gentle collisions, gradually building larger and larger clumps. These clumps grow into pebbles, then boulders, then asteroids, and eventually, planets. The process takes millions of years. Rocky planets like Earth form in the inner regions of the disk, where temperatures are warm enough to vaporize ices. Gas giants like Jupiter form farther out where ice can survive, providing extra solid material to build massive cores that then attract thick atmospheres of hydrogen and helium. Our Sun formed 4.6 billion years ago from a molecular cloud that probably also gave birth to thousands of other stars. Those sibling stars have long since drifted apart, scattered throughout the Milky Way by the galaxy's gravitational tides and their own random motions. Somewhere out there, perhaps hundreds of light years away, are stars that formed from the same cloud as our Sun, that condensed from the same collapsing core region, perhaps only a few light years away from the protostar that became our Sunday. We'll probably never identify them with certainty, these distant cousins lost among the hundreds of billions of stars in our galaxy. The most massive stars, those with 50 or 100 or even 200 times the Sun's mass, face special challenges during formation. Their immense luminosity produces such intense radiation pressure that it should blow away in falling material, preventing them from growing larger. Yet these monster stars clearly do form. Astronomers think they form through a process called competitive accretion, where a forming star in a dense cluster gravitationally captures material that was heading toward its neighbors. The more massive it becomes, the more material it can steal, growing rapidly at the expense of nearby forming stars. Sometimes, star formation produces unexpected outcomes. In crowded stellar nurseries, young stars can gravitationally capture or exchange planets, or even steal entire protostellar disks from one another. Close encounters can fling planets into interstellar space, creating rogue worlds that drift through the galaxy without any star to orbit. These interactions might explain why some planetary systems we've discovered have such strange arrangements. Giant planets in very close orbits, planets moving backward relative to their star's rotation, or multiple planets with wildly tilted orbits. Stars born in different environments develop differently. A star forming alone in an isolated dark cloud will evolve quietly, undisturbed, taking its full allotted time to contract and begin fusion. A star born in a massive cluster, surrounded by thousands of siblings, will experience a far more violent childhood, battered by radiation from nearby massive stars, perturbed by close gravitational encounters, possibly losing its protoplanetary disk before planets can form. The environment matters. Two stars with identical masses might follow very different paths depending on where they were born. The process of star formation enriches the interstellar medium even before the stars themselves explode. Stellar winds from massive young stars blow chemically enriched material back into space. These winds contain elements processed in the star's core through nuclear fusion and dredged up to the surface by convection. Even Tauri stars, though they haven't begun hydrogen fusion yet, contribute to this enrichment through their powerful outflows and jets. The galaxy is a vast recycling system where matter flows continuously between stars, gas, and dust. Recent calculations suggest the universe may contain as many brown dwarfs as stars. For every 6 stars in the galaxy, there might be one brown dwarf, cool and faint and difficult to detect. Most brown dwarfs remain undiscovered, hidden in the darkness. They represent a significant fraction of the galaxy's mass, a population of failed stars that came close to stellar status, but fell just short. Some drift alone through interstellar space. Others orbit stars as companions, easier to find because the gravitational influence of their parent star reveals their presence. A protostar's surrounding disk doesn't last forever. Over time, material either falls onto the protostar, gets blown away by stellar winds, or gradually dissipates back into space. Within about 5 to 10 million years, most disks are gone or reduced to thin debris, disks containing only rocky material and ice. If planets haven't formed by then, they won't form at all. This puts a time limit on planet formation. Our solar system's planets had to coalesce from their disk within those first few million years of the Sun's existence. The study of star formation connects to fundamental questions about existence. How did our Sun form? How did Earth come to be? Are we alone in the universe, or do other planets orbit other stars born from other molecular clouds? Every answer leads to new questions. Each discovery opens unexpected doors. The infrared glow of a distant protostar carries information about processes that happened in our own solar system billions of years ago. By studying stellar birth across the galaxy, we're looking both outward into space and backward into time, tracing the processes that created our Sun, our planets, and the elements that make up everything around us. Let each breath guide you to realize time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second, you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. Light takes time to travel. When we observe a star forming 1,000 light-years away, we're seeing it as it was 1,000 years ago. The protostar we're watching might already be a full-fledged star by now, its disk dispersed, its jets silenced. We're always looking into the past when we look into space. Every observation is historical. The present moment of distant objects is forever hidden from us, separated by the finite speed of light. Time and space are intertwined in ways that can feel both profound and wonderfully peaceful. The coldest molecular clouds are also the darkest. Not just dark in visible light, but dark across nearly all wavelengths. They block, absorb, or scatter almost every photon that tries to pass through them. Within their centers, the darkness is absolute, unbroken by any light from outside. These are regions where the universe comes closest to achieving perfect blackness, perfect stillness. And yet, within that darkness, the slow dance of gravity pulls matter together, building the seeds of brilliant future stars. Star formation is inefficient but persistent. Most of the gas in a molecular cloud never becomes part of a star. It drifts back into space, redispersed by energy from the stars that did form. But that scattered gas doesn't disappear. It mingles with other gas between the stars, cools again over millions of years, perhaps joins another molecular cloud somewhere else in the galaxy. The cycle continues. Formation, dispersal, reformation. The same atoms participate in multiple generations of stellar birth across billions of years. Every star we see in the night sky was once a protostar hidden in dust. Every point of light overhead began as a collapsing core in some ancient molecular cloud. The process that created them is the same process happening right now in nebulae scattered throughout the galaxy. Stellar birth hasn't stopped. It continues in the present, though at a slower rate than in the past. New stars are being born tonight, this very moment, invisible to us, but real nonetheless. Protostars grow by accretion, pulling in matter from their surroundings. The rate varies but averages roughly 1/1,000,000th of a solar mass per year for a sun-like star. That sounds tiny, but sustained over 1,000,000 years, it builds an entire star. Growth happens slowly, imperceptibly, through countless small additions. There's something almost meditative about imagining this process, material spiraling inward grain by grain, molecule by molecule, building something vast through patient accumulation. Stars form slowly. Rushing is impossible. The transition from protostar to star isn't sudden. There's no single moment when fusion begins everywhere at once. Instead, fusion starts in the very center of the core, in the hottest, densest region. It then gradually expands outward as surrounding layers heat up sufficiently. The protostar doesn't suddenly turn on. It gently transitions from one state to another, crossing from youth to adulthood so gradually that pinpointing the exact boundary is arbitrary. Nature favors smooth transitions over sharp boundaries. Deuterium, the heavy isotope of hydrogen that brown dwarfs fuse, was created in the Big Bang itself. It's primordial, left over from the first few minutes after the universe began. Brown dwarfs burn through their deuterium quickly, within 10 million years or so, and then it's gone. No more deuterium is created inside stars through normal fusion processes. Each brown dwarf is consuming a small portion of the universe's original supply, matter that has existed unchanged for nearly 14 billion years until now. The more we learn about star formation, the more questions arise. Why do some clouds form stars and others don't? What determines the masses of individual stars? How common are planetary systems? How frequently do Earth-like worlds form? Each answer reveals new layers of complexity, new variables to consider, new observations needed. The universe resists simple explanations. It invites endless curiosity, endless study, and that invitation feels less like frustration and more like a gift of infinite wonder. Jets from protostars can be remarkably straight. Some extend for several light years in nearly perfect lines, despite having been ejected over thousands of years, during which the protostar itself might have moved or wobbled. The straightness suggests that magnetic fields guide the jets. keeping them collimated, preventing them from spreading out. These magnetic channels through space remain stable even as everything else around them changes. It's a strange kind of stability in the midst of chaos, order emerging from turbulence. Some molecular clouds are enormous, containing 1,000,000 times the Sun's mass. Others are tiny, barely enough to make one small star. The universe offers the full spectrum of possibilities. The largest clouds can birth thousands of stars in massive clusters. The smallest might form only a single, isolated star. Both outcomes are valid, both are natural. Scale varies tremendously, yet the basic physics remains the same. Gravity, pressure, heat, magnetic fields, the same ingredients in different proportions yield different results. Star formation is louder than you might think, in a sense. The jets, winds, and shock waves from forming stars create turbulence that shakes the surrounding gas, generating pressure waves. If space weren't a vacuum, if there were air to carry sound, stellar nurseries would roar with constant noise. But in the silence of space, these processes unfold mutely, seen only through light and inference, heard only in our imagination of what those vibrations might sound like. Observations suggest that most stars form in groups, but that most stars we observe today are alone. This apparent contradiction resolves when we realize that stellar clusters gradually dissolve. Over hundreds of millions of years, gravitational interactions slowly eject stars from their birth clusters. Some gain just enough velocity to escape. Others experience close encounters that fling them outward. Eventually, the cluster disperses entirely, its members scattered. Community births, solitary lives. It's a pattern repeated throughout the galaxy. There's speculation, though it's personal reflection rather than proven fact, that the process of star formation mirrors other forms of growth and creation throughout nature. Small beginnings accumulating into something larger, chaos gradually resolving into order, simple components combining into complex systems. Whether it's stars, life, thoughts, or galaxies, the patterns feel similar. This is subjective interpretation, not science, but the resemblance across scales can spark wonder, connecting the cosmic to the everyday. Protostars hidden in dark clouds sometimes announce themselves through outbursts. The accretion rate suddenly increases dramatically for reasons not fully understood. Material crashes onto the protostar in a sudden flood, and the protostar brightens by factors of 10 or 100, emitting intense infrared radiation. These outbursts can last for decades or centuries before fading. They're unpredictable, reminders that even in the slow process of stellar birth, sudden changes can occur without warning. The earliest stages of star formation might be impossible to observe directly. Before a protostar exists, there's only a collapsing core, still cold, still dark, emitting almost no radiation. Telescopes can detect these cores only by their absorption of background light or by faint traces of radiation from cold dust. We infer their existence more than we observe it. Some processes in the universe remain nearly invisible, knowable only through indirect evidence and careful reasoning. When a massive star finally explodes as a supernova, it releases more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. That energy blast can compress nearby molecular clouds, triggering new star formation. In this way, death leads directly to birth. The end of one star creates conditions for others to begin. The cycle is eternal, at least for now, while the universe still has gas to form stars. Eventually that too will end, but that ending lies trillions of years in the future. Some stars are born already moving fast, ejected from their birth clusters by gravitational interactions before they even finish forming. These runaway stars travel through the galaxy at high speeds, sometimes creating bow shocks, where their motion compresses the thin interstellar gas ahead of them. They're emigrants, departing their communities of origin almost immediately, destined to wander alone. Their existence raises questions about fate, randomness, and whether outcomes are predetermined or accidental. The initial mass function describes how many stars of each mass are born. Nature produces far more low-mass stars than high-mass stars. For every star like the Sun, there are roughly a dozen smaller stars. For every star 10 times the Sun's mass, there are thousands of Sun-like stars. The most massive stars are exceedingly rare. This distribution appears universal, the same in every star-forming region we've studied. Why nature follows this pattern remains unclear, but the consistency itself is intriguing. As our instruments improve, the line between protostar and planet becomes blurrier. We discover objects in the transition zone, too massive to call planets, too low mass to call stars. These borderline objects challenge our categories, forcing us to acknowledge that nature doesn't respect the boundaries we create. Definitions serve us, not nature. The universe simply produces objects across a continuous range of masses. Our need to classify them is ours alone, not inherent to the cosmos. Star formation transforms the appearance of galaxies. A galaxy experiencing a burst of star formation glows brilliantly with the light from young massive stars. As that burst fades, the galaxy dims, aging as its stellar population ages. Spiral galaxies maintain ongoing star formation in their arms, staying blue and bright. Elliptical galaxies have exhausted their star-forming gas, fading toward redness as their oldest stars dominate. Galaxies age not just through time, but through their history of creating and ceasing to create new stars. The first protostar to form in a molecular cloud might influence where and when others form. Its jets could compress nearby gas, triggering secondary collapse. Its radiation might heat the cloud, preventing further formation. Or its formation might have no effect on distant regions, each core collapsing independently on its own schedule. The degree of correlation between different formation sites within a single cloud remains an active research question, studied through observations of many stellar nurseries. Protostars don't just pull in gas, they also pull in dust, and with dust comes any larger solid objects, like small asteroids or comets, that might exist in the cloud. Material that formed elsewhere, perhaps around an older star that died millions of years earlier, can be incorporated into new stars and their planetary systems. Your body contains atoms from multiple generations of stars. Every breath connects you to a history stretching back billions of years and across countless light-years of space. Tauri stars vary in brightness on timescales from hours to years. Material from the accretion disk falls onto the star in irregular clumps, causing brief brightenings. Star spots, like sunspots but larger and cooler, rotate in and out of view as the star spins rapidly, creating periodic variations. Occasionally, larger outbursts occur for reasons less well understood. Watching a Tauri star over time reveals a restless, turbulent youth, slowly settling toward calmer middle age. Among the most beautiful objects in astronomy are Herbig Haro objects, the glowing nebulae created when protostellar jets collide with surrounding gas. They glow in vibrant colors, reds, greens, blues, depending on which elements are emitting light. Their shapes are intricate, organic, almost biological in appearance, with curves and loops and filaments. They change over human timescales, visibly shifting and evolving over decades. They're temporary art, cosmic paintings that exist briefly before fading back into darkness. In the end, star formation is a balance. Gravity pulls inward, pressure pushes outward. Both forces are necessary. Too much gravity and matter would collapse immediately into black holes. Too much pressure and clouds would never collapse at all. The universe provides exactly the balance needed for stars to form at a measured pace over billions of years. Whether this balance is accidental or meaningful is a question science cannot answer, but you may draw your own conclusion. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Stars are born from clouds. Clouds form from dispersed gas. Gas is expelled by dying stars. Those dying stars were born from earlier clouds. All are circles, cycles, endless orbits, like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. The word nebula means cloud or mist in Latin. Early astronomers saw fuzzy patches in the sky and called them nebulae, not knowing what they were. Some nebulae are galaxies, entire collections of billions of stars appearing diffuse because of their vast distance. Others are true clouds of gas where stars form. We now distinguish between them, but the old name persists. Language carries history, preserving the wonder of those who first looked up and wondered what they were seeing. Protostars are patient. They don't rush. Millions of years pass as they gather mass, grain by grain, slowly enough that nothing seems to change from one century to the next. Human lifetimes are invisibly brief compared to stellar timescales. To a protostar, our entire civilization exists in the blink of an eye, a flicker barely long enough to notice. Time means different things at different scales. There's something humbling and oddly comforting in that difference. When fusion finally ignites in a protostar's core, the star doesn't suddenly change appearance. The core begins fusing hydrogen, but that energy takes thousands of years to work its way outward through the dense stellar interior before reaching the surface and escaping into space. The star's outward appearance lags behind its internal transformation. What is real at the center and what appears real at the surface are separated by time. Truth travels slowly through matter. Some stars will live for trillions of years. The smallest red dwarfs, those with only about 10% of the sun's mass, burn their fuel so slowly that they'll outlive every other type of star by vast margins. The universe isn't old enough yet for any of these tiny stars to have completed their lifespans. Every small red dwarf ever born is still shining. Longevity comes from moderation, from burning gently rather than brightly. A protostar's disk is a place of constant motion. Material orbits, spirals, collides, accretes. Dust grains stick together and break apart. The disk is neither solid nor empty, but something in between, a place where matter transitions from cloud to planet, from chaos to order. Within that disk might be the seeds of future life, the materials that will eventually become living cells, thoughts, consciousness. All of it begins in the disk around an infant star. The universe produces variety. No two stellar systems are quite identical. Each begins with slightly different initial conditions, a different mass, a different spin, a different chemical composition. Those tiny differences amplify over time, producing the astonishing diversity we observe. Some planetary systems have gas giants close to their stars. Others have them far away. Some have Earth-like planets. Others have none. The same basic process yields endless variation. Watching star formation across the galaxy connects us to something larger than ourselves. These processes happen whether we observe them or not. They happened before humans existed and will continue long after we're gone. The universe doesn't require our attention, yet we give it anyway, compelled by curiosity and wonder. There's a kind of humility in studying something so vast and indifferent to our existence. And paradoxically, that humility feels uplifting rather than diminishing. Brown dwarfs might have been more common in the early universe when conditions were different. The first molecular clouds contained only hydrogen and helium, with no heavy elements. Calculations suggest that clouds lacking heavy elements fragment more readily into smaller pieces, potentially producing more low-mass objects and brown dwarfs. If true, the ancient universe might have been full of failed stars, their faint light contributing to the dimness of early cosmic epochs. Stars born in the same cluster gradually drift apart over time. but they carry traces of their shared origin. They have similar chemical compositions, similar ages, similar velocities through the galaxy. Astronomers can sometimes identify these dispersed siblings by detecting those subtle similarities across many stars. It's like finding distant relatives through genetic testing, recognizing kinship in the data, even when all other connections have been lost to time and distance. The coldest temperature possible is absolute zero, negative 459.67 degrees Fahrenheit. Molecular clouds approach but never quite reach this limit. At these extreme colds, matter behaves strangely. Molecules move sluggishly, chemical reactions slow nearly to stopping. Yet even in such cold, gravity continues working, unchanged, pulling matter together. Gravity is patient, implacable, indifferent to temperature. Cold cannot stop it. Nothing can, except the outward force created when matter becomes dense and hot enough to resist. Infrared astronomy has revealed so much. Before infrared telescopes, entire regions of star formation were invisible, known only through inference. Now we can see inside the dust, watch protostars evolving, measure temperatures and densities directly. Technology extends perception, letting us sense wavelengths our eyes cannot detect. What we see depends on our tools, and what we understand depends on what we can see. Each technological advance opens new windows on reality. Some protostars are found alone in dark clouds, far from any other forming stars. They collapse in isolation, surrounded by emptiness. Their loneliness is absolute, separated from the nearest stellar neighbor by multiple light-years of nothing. Yet they follow the same process as stars born in crowded clusters. Location changes experience, but not fundamental nature. Whether alone or surrounded, gravity and pressure follow the same physical laws, producing the same eventual outcomes. When the Sun formed 4.6 billion years ago, the universe was already 9 billion years old. Stars had been forming for most of cosmic history by that point. The Sun is a relative latecomer, born in an enriched galaxy that already contained multiple generations of previous stars. The atoms that make us existed before the Sun cycled through earlier stars, dispersed by ancient supernovas. We're made from recycled stardust. Everything is recycled. Nothing is truly new. A protostar surrounded by a disk looks like a spinning figure skater. The rotation inherited from the molecular cloud gets concentrated as the cloud collapses. Conservation of angular momentum demands this. The mathematics are simple, but the result is profound. Matter, spinning in space, creating beautiful spirals and disks. The same physics that makes skaters spin faster when they pull in their arms makes protostars rotate and form planetary systems. Turbulence in molecular clouds creates structure on every scale. Large eddies spawn smaller eddies. Small eddies create even smaller swirls. This cascade continues down to the smallest scales where individual particles collide. From light years to molecules, motion exists at every level, interconnected, self-similar. It's a kind of fractal complexity, patterns repeating at different sizes. Nature seems drawn to this layered intricacy, choosing complexity over simplicity whenever both are possible. A subjective reflection, watching protostars form, feels like witnessing creation itself, not in a religious sense necessarily, but as a fundamental act of bringing something new into existence. Matter that was diffuse becomes concentrated. What was dark begins to glow. Potential transforms into reality. It's a slow miracle, if miracles can be slow. The universe continuously creates itself, renewing itself, generating novelty from ancient material through processes as old as time. The interstellar medium, the gas between stars, is not uniform. It's full of structure, bubbles, shells, filaments, clouds. Previous generations of stars have shaped this structure through their winds and explosions. Star formation doesn't happen in pristine gas, but in material already processed by earlier events. The universe has memory in a sense. Current events reflect past events. Everything is connected through time, through cause and effect, through the cycling of matter. When protostars eventually disperse their natal clouds through radiation and winds, they expose themselves to view. The young stars emerge like butterflies from cocoons, transformed from hidden embryos into visible objects. That first light, after millions of years hidden in dust, marks a transition. The star's visible life has begun. Its formation phase is ending. Soon, it will reach the main sequence and settle into the long, stable phase that follows. In the grand scheme, stars are temporary. They're born, they live, they die. Billions of years is a long time by human standards, but finite nonetheless. The universe existed before any particular star, and will exist after that star is gone. Yet, during its existence, each star is real, complete, present. Temporary doesn't mean meaningless. Duration doesn't determine significance. Brief things can matter. Stars teach us that impermanence and importance can coexist. Only about 2% of the mass of a molecular cloud is ever involved in active star formation at any given moment. Most of the cloud is diffuse background material, supporting structure but not directly collapsing. The actual formation happens in tiny, dense cores embedded within the larger cloud. Creation is concentrated, focused, happening in specific places, while most of space remains unchanged, providing context but not participating directly in transformation. The jets from protostars can be traced back to their source. Astronomers follow the jet backward, looking for where the two sides of the outflow converge. At that convergence point lies the protostar itself, often still completely hidden in dust. The jets become signposts, pointing to invisible objects. What cannot be seen directly can still be found through its effects on surroundings. Invisible doesn't mean undetectable. Truth reveals itself through consequences, through influences, through the patterns it creates. As protostars age, they spin down. They're born rotating rapidly, but gradually lose angular momentum through magnetic braking and mass loss. The Sun, once formed, probably rotated much faster than it does today. Over billions of years, it slowed. This slowing is inevitable for all stars. Nothing escapes time's effects. Everything changes, gradually, through processes that operate on timescales too long for individual humans to witness, but real nonetheless. If you could watch a molecular cloud collapse into a star in fast forward, compressing millions of years into minutes, you'd see something remarkable. The cloud would shrink, darken, then brighten at the center. Jets would burst outward. The surrounding material would spiral inward. Finally, the dust would clear, revealing a young star where before there was only empty darkness. It would look like magic, but it's physics, proceeding inevitably from initial conditions to final outcome. Every star you see in the night sky has a story, each formed in its own molecular cloud, at its own time, under its own circumstances. Some are young, just beginning their lives. Others are ancient, born when the universe was a fraction of its current age. They're scattered across space and time, yet all visible in a single glance upward. The night sky is a museum of stellar origins, displaying births separated by billions of years. Perhaps the most humbling fact about star formation is that it continues regardless of whether we understand it. Our knowledge improves, our questions become more refined, but the process itself is unchanged by our attention. Stars formed before we existed to study them. They'll form after we're gone. The universe is indifferent to our curiosity, yet that indifference somehow makes the act of studying it feel more meaningful, more precious, more worth doing. And so, our quiet journey through stellar nurseries comes to a gentle close. We've traveled from vast molecular clouds stretching across hundreds of light years, to tiny cores collapsing under their own gravity, to protostars hidden in cocoons of dust, to the moment when fusion finally ignites and a star, is truly born. We've glimpsed how patient the universe can be, how millions of years pass as matter slowly transforms from cloud to star. From invisible darkness to brilliant light, we've discovered that creation happens everywhere, constantly, following laws as old as time itself. Stars remind us that beginnings can be slow and hidden, that what emerges into light often spent eons preparing in darkness. That accumulation, patience, and time can transform even the most diffuse matter into something dense and brilliant. Without stars, there would be no heavy elements, no planets, no life. By studying their birth, we understand our own origins. By pausing to notice, we glimpse the extraordinary in the ordinary. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity, of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in a star's core, where all boundaries dissolve. Light, matter, energy, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity, pulling you into sleep. Prepare for deep sleep. No boundaries left, only peace. If this gentle journey through stellar birth brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, through space and time, through clouds and cores and jets and disks. You can allow these thoughts of star formation to fade now, like dust dispersing after a protostar's winds have cleared the cloud, leaving only the gentle calm behind. Let your breathing deepen. Let your body feel heavier, as if gravity itself were pulling you down into the bed, into the earth, anchoring you safely. If sleep comes, let it carry you like matter spiraling into a protostar, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, stars will still be forming in molecular clouds across the galaxy. Protostars will still be pulling in matter grain by grain. The universe will continue its slow work of creation. But tonight belongs to stillness. Rest well, sleepy astronomer. And remember, you are made from stars, and to the stars you may one day return. Dream deeper with bedtime science. Good night.